Hi everyone, I'm Wang Rui, and today I'll introduce our work GDKVM, a novel architecture for echocardiography video segmentation. I will first describe the problem setting, then introduce our method, followed by experiments and discussion. So, what is the main challenge we are dealing with? In medical imaging, noise is unavoidable, contours are often unclear, and the heart changes dramatically as it beats. These variations make reliable analysis very difficult. When it comes to videos, the challenge grows further. Long temporal contexts are hard to capture, and we constantly face a trade-off between accuracy, efficiency, and computational cost. Finally, in clinical simulation, there is no ground truth available during inference. This means the model must rely on boundary frame prediction during training in order to compute the loss. Our goal is to reduce computational cost and improve robustness in noisy echocardiography data. The key encoder extracts fused spatial features, while the value encoder incorporates both the current frame and the previous prediction. Together, they form a hidden state that evolves over time. The update step is dynamic. We use data-dependent matrices to decide how much new information should be written in, and how much outdated memory should be discarded. During inference, the model relies only on this state and the query frame, without ground truth, which makes it closer to real clinical practice. Traditional methods for medical video segmentation often depend on softmax attention or naive memory banks, which are inefficient and less accurate. To overcome this, we introduce the linear key-value association, which linearly updates features frame by frame, reducing complexity from quadratic to nearly linear. This enables real-time analysis while still capturing long-range temporal dynamics of cardiac motion. On the spatial side, we design a key pixel feature fusion module, which integrates local features, global context, and fine-grained pixel details. This is especially important for clinical ultrasound, where speckle noise and artifacts are common. Yet preserving small structures like valve motion is essential for accurate diagnosis. A major challenge in long video tasks is how memory is represented and updated. While LKVM improves efficiency, it still struggles with complex frame-to-frame variations. To address this, we introduce the gated delta rule, which allows the model to manage memory more effectively. Here, the data-dependent matrix beta controls the strength of writing new information during memory interactions, while alpha controls how quickly outdated content is forgotten. We also visualize how alpha and beta evolve during training. When the frame contains structural shifts, beta increases to capture important details. When the frame is noisy or blurry, alpha strengthens, forgetting to remove interference. We benchmark GDKVM against both task-specific and general video segmentation models. Existing methods often depend on heavy memory or attention mechanisms, which struggle with spatial complexity and computational load. On two large echocardiography datasets, our method consistently achieves the highest accuracy while running in real time. Moreover, when estimating the left ventricular ejection fraction from segmentation results, GDKVM achieves the strongest correlation with ground truth and the lowest measurement bias, showing clear clinical relevance. Here we present a visual comparison with state-of-the-art methods. Previous models often produce incomplete or excessive masks. Our method maintains anatomical fidelity and cleaner segmentation results. Looking ahead, there are three main directions we plan to explore. First, extending GDKVM to broader ultrasound datasets will help verify its generality across different clinical environments. Second, we aim to tackle longer video sequences, irregular heart rhythms, and more complex pathological cases. Finally, optimizing the matrix state for parallel hardware acceleration will make the model more scalable and practical in real-world applications. Thank you for your attention.